Welcome to topic 4 of CP1. In this topic, we're going to cover 2-pointers and sliding window. So these are related techniques. So sliding window can be viewed as a special case of 2-pointers. And 2-pointers are, just as the name indicates, one maintains 2 pointers into arrays. Oftentimes it's a single array. You have 2 pointers pointing to 2 different positions, and then you move these 2 pointers. It could also be 2 different arrays. So you have one pointer pointing to one array, another pointing to another array, and you move these pointers based on the values that they point to. It turns out that this is a very basic technique, but it can be fairly powerful. So it can be used in surprising ways, and we're going to see some example problems that use 2 pointers. So the first example problem that I want to talk about is this lead code problem called 2sum2. So this is a 2sum problem, but this has a condition that the input array is sorted. So let's look at the problem description. So we are given an array of integers that is already sorted in ascending order, and we are asked to find 2 numbers such that they add up to a specific target number. So yeah, there's some extra conditions. So we can assume there's exactly one solution. So this is just to make the problem simpler. So the general solution doesn't really need this. And the restrictions, you may not use the same element twice. So if a double of one element equal the target, that doesn't count. So let's look at the sample. So this is the array here, and the target is 11. And well, you can stare at it a little bit, but the only solution is 2 plus 9 equals 11. And for this particular problem, you are supposed to output an array of 2 elements, 2 and 4, because these are the indices of the 2 elements. And in this problem, the indices start at 1 instead of 0. So this is the second element, this is the fourth element. So that's what this problem. So I assume you already know the 2sum problem, and you know how to actually solve this problem in linear time using some actual storage. So if you don't know, you should pause the video, think a little bit about how to solve that. So that approach is anytime you see a number, you put that number into a set, for example, into a hash set. And then anytime you see a number, for example, if I see 7, I know I need a 4 in order to make it. So I look into the set to see whether a 4 has been seen. So I guess if we want the indices here, so then actually what we need to put into the set is actually, well, I guess one way to do it is we put in a pair, the value and the indices. Or if we are really lazy, we can just put in the value, and then if we know it exists, we can always scan the array again to find it. So that is actually linear time. However, that approach requires extra storage. So these problems can be solved without any extra storage efficiently when it's already sorted. So if you want to solve this problem without extra storage, then the first thing you do is you sort it, then you have n log n. But after sorting it, there is actually a linear time solution. So of course, the worst case, the brute force method is to consider all pair and see whether they sum up to the target. And the key idea that enables us to reduce the complexity from n squared to linear time to n, to big O n, is we don't have to consider all pairs of the numbers. So let's have the 2 pointer pointing, 1 point to the beginning, 1 point to the end. So for this array, we have 1 and 15. So when we add it up, we find out that it's too big. So it's bigger than the target. Now, at that moment, knowing that 15 plus 1 is too big, that actually tells us 15 can never be any part of the be part of any solution, because 15 add this number 1 is already too big. So because the array is sorted, any of the other number that we haven't checked will be too big. So when we add it to 15, that will be too big. So then actually we can move the second pointer from 15 to 11. We know that 15 doesn't need to be considered again. So when we have 1 plus 11, that's still too big. So then we'll move the pointer, instead of pointing to 11, we move it to 9. So at this point, we have 1 plus 9, which is too small. Now, if it's too small, then we know 1 cannot be matched with any number, be paired with any number to create 11. Because it cannot, the number that we already scanned on the right side, we know it doesn't already, we already know it doesn't work. But if for any number less than 9, certainly it wouldn't work to pair it with 1 to get 11, because 9 is already too small. So any number we haven't checked is already too small. So there's no solution involving 1. So then we can move the pointer, the left pointer right. So then we get 2. So we have 2 plus 9 that give us the solution, and then we can return. So of course, if the array have more than one solution, we can just continue scanning through to find all the solutions. So the key insight is we don't have to consider all pair of numbers. When we consider the pair sum up, if it's too big, then we know that the bigger number cannot be paired, so we can move the right pointer. If it's too small, we move the left pointer. So this is implemented in this logic. So we have 2 pointers, first and second. The first one point to 0, second point to the last element. And then while we do this loop, we compute the sum. If the sum is too big, we move the right pointer. If the sum is too small, we move the left pointer. We increment the left pointer. Otherwise, the sum is equal, then we're done. We find our 2 elements that sum up to this target. So the question I have on the slide is what goes on here? So what condition should we use? And the second question is, what is the time complexity of this algorithm? So we said it's big O(n), it's a linear time, but I want you to kind of be able to argue why it is a linear time. So if you want, you can pause the video and think about it. So line 3, the condition should be while first is less than second. Because the moment they meet, we know we have checked everything that could be checked. We should get out, because this problem doesn't allow us to use the same element twice. If they allow us to use same element twice, then the condition should be first less than equal to second, because we do want to consider when they overlap, they point to the same element. Maybe that element double will equal the target. But if they switch, if the first become bigger than second, then definitely we should get out. But for this case, this problem, because they don't allow using the same element twice, should be first less than second. And the complexity is linear because this loop, every time we go through this loop, one of 3 things must happen, right? So either second will be decremented by 1, or the first will be incremented by 1, or we actually are done, we just return. So then this loop can execute at most n times. And here, every line is just a basic operation. So the complexity is big O(n). So that's it for this problem.